We need to venture a little further into physics for a bit because there's some physics that we have to understand so we can understand the chemistry. One of those concepts is the nature of light. So light is a form of electromagnetic radiation. Electromagnetic radiation is composed of oscillating waves, two of them, an electric field and a magnetic field. The electric field is a region in which an electrically charged particle, such as an electron or a proton, would experience a force. A magnetic field is where a magnetized particle experiences a force. Magnetic fields and electric fields are similar in some ways, and yet they are fundamentally different. All of these electromagnetic waves move through space at the same speed. It's known as the speed of light, and that's 3 × 10⁸ meters per second. That's very, very fast. So here's an illustration of the fields in electromagnetic radiation. So we have the electric component. So it's a wave that's oscillating, going up and down. And this radiation is traveling in this distance at the speed of light. And then perpendicular to that, we have the magnetic component oscillating. They have nodes at the same place and peaks at the same place, but they're oscillating at 90 degrees to each other. You probably are aware that sound travels slower than light does. You see this in fireworks. You see the flash, and then you hear the pop or the boom. We see this with thunder and lightning. We see the lightning, and later we hear the thunder. Because the sound is traveling around 340 meters per second, and the light is traveling at 3 × 10⁸ meters per second. And you can actually gauge how far a storm away is by measuring the time between when you see the flash and when you hear the sound. We need to understand how waves are characterized, and this applies to electromagnetic waves, but also to ocean waves and vibrating guitar strings and all sorts of things like that. The amplitude is the height of the wave, the distance from the node, the 0 point to the crest, or from the node to the trough. It's a measure of light intensity if we're talking about light. The larger the amplitude, the brighter the light. If the light is dim, the amplitude is lower. And wavelength. Wavelength is given the symbol lambda, the Greek letter lambda, and this is a measure of the distance from one crest to the next. How long is the wave? That's the wavelength. So here's an illustration. The amplitude, we see this is a wave going up and down, and it's crossing this median line. And where it crosses, these are called nodes. So the amplitude is the distance from one node to the peak or from a node to the trough. It's going to be the same. And the wavelength is from peak to peak or from this node, skip that one to this node, alternating nodes. Another characteristic of waves is the frequency, and this is given the Greek letter nu, which unfortunately looks a lot like a V, but it isn't. It's slightly curvy. That's the number of waves that pass a point in a given period of time. So it's the number of waves or the number of cycles. So you may have heard of a unit like Hertz, not the rental car company. Hertz means cycles per second. Cycles per second, or sometimes it's just called per second. Things per second. How many times does it happen in a second? And so that's the frequency. Do I have a picture coming up? I don't. I'll have to draw one then. So let's think about a wave. So here we have a wave coming at us, and we're standing here. And to measure the frequency, you measure the number of peaks that pass a given point in a second. So you're standing here and the wave's coming at you and you're counting. You can imagine standing at the ocean and the waves are rolling in. Now there the frequency is going to be less than 1 per second, but you could count for a minute and divide and find out what that fraction is. But you're counting the number of waves coming in per second. The thing is that the radiation is moving at the same speed. So if we have a long wavelength, we're going to have a low frequency because there's not a lot of waves coming in. If I change this and make this a short wavelength, now in that same period of time, I'm going to get more waves to count, right? The frequency is higher. The amplitude could be the same. The velocity is definitely the same. But the wavelength and the frequency are related. So the frequency and the wavelength are related. The total energy is proportional to the amplitude of the waves and their frequency. So if you think about standing maybe waist deep in the ocean, have all of you been to the ocean? It's not a guarantee, even though we're only 3 hours. It's sad, but a lot of people don't get a chance to go to the ocean. If you haven't had a chance, you should go if you get a chance. The waves are coming in. If it's a calm day and the waves have a low amplitude, they break on you and it's okay. You feel the force of them. If it's a stormy day and the waves have high amplitude, they might knock you down. There's a lot of energy in the wave of water coming at you. And that energy depends on the amplitude, how tall the wave is. It also depends on the frequency, right? If the waves are just slamming into you, bang, 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 that's a lot more energy than if they're coming at you and hitting you, bang. And then you wait, and then another one comes, bang, right? So thinking about waves of water can help us to understand these concepts that we need to understand for waves of electromagnetic radiation. Waves traveling at the same speed, shorter wavelength is going to pass more frequently. More waves per second, higher frequency. So the wavelength and frequency are inversely proportional. If the wavelength is long, the frequency is short, and vice versa. We know that the speed of light is constant, and so we have this relationship. The frequency is equal to the speed of light divided by the wavelength. The speed of light is meters per second. The wavelength, let me write that out. The wavelength could be measured in meters. So if we have meters per second divided by meters, then the units work out to 1 over seconds, which is the unit of frequency. How many per second? So this is a good relationship to remember. So dim light is going to have a lower amplitude, and bright light is going to have a larger amplitude. So amplitude is brightness. The wavelength is different colors of light. That's how our eyes perceive it. So red light is going to have a longer wavelength. Longer wavelength is going to be lower frequency. And yellow light will be in the middle, and blue will be a shorter wavelength, higher frequency. So we said that energy depended on the amplitude and the frequency, right? So think about ocean waves coming at you. Which is going to transmit more energy to you, this red light or the blue light? The blue one. Their amplitudes are the same here, but this one's coming at you. It's hitting more frequently. The speed of the light is the same, but because it's oscillating up and down faster, it carries more energy. So color is determined by the wavelength. what we perceive as white light is actually a mixture of all the colors of visible light. It's known as a spectrum. And in white light, we have these colors: red, orange, yellow, green, blue, indigo, violet. To remember that, I was taught Roy G. Biv. Roy G. Biv. Like some weird name, I guess. And the colors, as we see in this picture, are always in that same order: red, orange, yellow, green, blue, indigo, violet. That's why when a child draws a rainbow, they've got a curve, they've got all the colors in there, and you're like, that was fabulous. You look at it and you're like, there's something wrong with that rainbow. Because they don't know the order of the colors, and so they may have put them in randomly. And you recognize that it's not right, but you may not realize why it's not right. They're always in the same order. When we see an object as a given color, like this girl has a red shirt, what's happening is, as the white light comes, the shirt is absorbing a lot of that energy, and it's reflecting the red wavelengths of energy. And so the red wavelengths come to our eyes, and we see red. My jeans are blue, okay? They're blue because they're absorbing most of the colors and reflecting blue light. And so that's how we see color. So let's do an example here. We can do calculations with wavelength and frequency and et cetera. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. Well, what have we learned this morning? We've learned that the frequency is equal to the speed of light divided by the wavelength. This is the wavelength. It says wavelength of, right? Lambda is equal to 515 nanometers. Do you remember what the speed of light was? 3.00 times 10 to the 8th meters per second. Well, we can plug these into that equation. In the numerator, we're going to have 3.00 times 10 to the 8th meters per second. In the denominator, we're going to have 515 nanometers. Now, what happens with the units? Are those going to work out? We're going to end up with meter per nanometer second. What unit do we want for frequency? Per second. We just want 1/second. We need meter and nanometer to cancel out. So we could do a separate calculation and convert nanometers into meters. Or instead of using the prefix nano, we can write what it means. So I'm going to erase this. Nano means 10 to the minus 9. So I'm just going to put in times 10 to the minus 9 meters, because this is the same as nanometers. So now we get out our calculators, which I so thoughtfully knocked mine on the floor for the second time just this morning. 3EE8 divided by 515 EE minus 9. And the frequency there is going to be, this would have 3 sig figs. 5.83 times 10 to the 14. We can write that as 1/seconds. We can write it as seconds to the minus 1, or we can write it as hertz. They all mean the same thing. 5.83 times 10 to the 14th hertz. That's a really high frequency, isn't it? There's no way you could count. Any questions? There's a relationship between the frequency, the speed of light, which is always the same, and the wavelength. So we've been talking about visible light. Visible light is only a little tiny piece of the electromagnetic spectrum. It's the portion of that spectrum that our eyes are able to detect. That's why it's called visible light. Shorter wavelength is going to be higher frequency. High frequency is higher energy. And then longer wavelengths, lower frequency, lower energy. And so at one end of the spectrum, we have radio waves. That same signal that comes to your radio and gives you the news is a form of electromagnetic radiation. And at the very high energy end, we have gamma rays. And then we have a variety of things in between. This high energy radiation is damaging, it's dangerous to biological molecules. Gamma rays are not good for your tissue. It's so high energy, they actually have a tool called a gamma knife that you can actually cut things with gamma rays. It's ionizing radiation. It causes molecules to ionize that your body would not like to be ionized, and so it messes things up. So here is the entire electromagnetic spectrum. So let's make some sense of all this. There's a lot of information in this one figure. Here we're seeing the frequency, nu, in hertz, going from about 10 to the 4th up to 10 to the 24th. So as we go to the right, frequency gets higher. As the frequency gets higher, the energy gets higher. And so we see that this end is high energy, this is low energy. Frequency and wavelength are inversely proportional. So this is the long wavelength, and this is the very short wavelength. This part down here is a blow up of this little tiny section in the middle. So here we see wavelength of light in nanometers, 750 for the red down to 400 for the violet. The violet has higher energy. That's this little portion in here. We have radio waves at the lower energy, microwaves, and yes, those are the same microwaves that heat your water for coffee in the morning in your microwave. There's infrared. The infrared is at the red end of this spectrum. There's ultraviolet, that's up here. Ultraviolet, it's above the violet. Then there's X-rays and gamma rays. Fabulous. Nephrared. Yeah, that's supposed to be infrared. Your book talks about these different types of radiation, and you should read that, but I don't see any point in me reading that to you. So you should look at that. Any questions about this figure? We can separate white light using a prism. It separates light according to its wavelength. And again, this is physics. It has to do with the different wavelengths of light and how they bend in this prism and bounce off of things. It causes them to separate. So here we have the long wavelengths and the short wavelengths. If we have a continuous spectrum, then we see a continuous rainbow. And we see this happen. It happens every afternoon when the sun hits the glass chandelier by the front door. And it makes these little tiny rainbows all over the room, and the kids think it's really cool. It happens when there's been rain. Do you remember what that is? We saw a little bit of it the other day. We get rain, and if there's droplets of water in the air and you're at the right angle with the sun, you see a rainbow in the sky. Sometimes you can see them when the sprinklers are going off in the yard too. The little water droplets are acting as prisms and separating the white light from the sun. This slide is probably not well placed. This is thermal imaging using infrared light. Infrared is longer wavelength than red light. We can't see it with our eyes, but we can make detectors that can detect it. And so you can take a picture of things in darkness and see them. And here what we're seeing as cold is blue. And so here, the background is blue. Red is warm. This guy's wearing shorts, and so we can see his legs and his face. We see the dog's eyes. And here we have evidence that dogs' noses are cold. That dog's nose is blue. And this this technology can be used for all sorts of things. And I don't know why it's in there right there. Yeah, these got messed up somehow. Okay, so electromagnetic radiation is waves, and waves can interact with each other. Waves interacting is called interference. And you can have constructive interference or destructive interference. When the waves are in phase with each other, they interact in a way that makes a larger wave. Destructive interference is when the waves are out of phase. The peak of one wave is lining up with the trough of another, and they'll cancel each other out. This is the principle for the sound deadening headphones. They actually are taking the sound in and shifting it so that it cancels out and makes the sound go away. It's the same idea that happens on a trampoline. If you're bouncing just right, one person doesn't bounce at all and the other person goes twice as high. It's the waves interfering, either constructively or destructively. So waves in phase mean that the peaks and the troughs match up, and then they add together. You can describe these waves mathematically as perhaps a sine function, and you can add them together. And the peaks are twice as big and the troughs are twice as low. If the waves come in out of phase and you're adding them together, they will cancel each other out. They add up to nothing, flat line. Waves also undergo diffraction. And what this is that when a traveling wave encounters an obstacle or an opening in a barrier, maybe there's a seawall and there's a little tiny hole that some of the wave can get through, they bend around the obstacle. This only happens if the barrier or the hole is roughly on the same size scale as the waves itself. Traveling particles do not diffract. If you throw baseballs through an opening, they don't diffract. They're particles, they just go straight through. But if you send waves through that opening, they will diffract and bend. And the diffraction of light between two slits, if that slit is, if they're separated by a distance that's similar in wavelength, we can get interference patterns caused by that diffraction. And this interference pattern is a characteristic of all light waves. I have a picture coming here. So waves, so here we have waves coming at this wall, and there's a hole here. There's a slit. This slit is about the same size as the wavelength. So when the waves come at this and go through, they're diffracted, and so they begin to curve like this. That's what diffraction is. If you have particles coming at that slit, particles that hit the wall will be stopped. Particles that go through will just go through. They don't get bent. There's a distinct difference between how particles and waves behave. If you take a light source, perhaps the sun, it is emitting light in all directions, and the wavelengths, the waves are in phase. They're lined up with each other. And so if we have two slits, and the distance here is on the scale of the wavelengths of the light, light hits here and diffracts, light hits at this slit and diffracts, and these waves now are in phase and will undergo destructive interference and constructive interference, and you'll get this pattern of bright and dark spots. When the waves are out of phase, you get a dark spot because they cancel each other out. When they're in phase, they make a bright spot. And we're going to watch another video now. So after watching this video, does this diagram make more sense? We can actually see it happen with the waves on the water. It's doing the same thing. The waves of light do exactly the same thing. So that demonstrates that light is a wave, right? Like he said, if it was a particle, you'd just see two bright spots. But because it's a wave, we see that fringing. Well, it turns out that light has a particle nature as well, and this is known as the photoelectric effect. It has been observed that many metals will emit electrons when a light shines on their surface. And it's called the photoelectric effect. Photo meaning light, and electricity, it kicks out an electron. Classic wave theory says that this is because the light energy is being transferred to the electron. If this were the case, only the amplitude, the intensity of the light, would affect the emission of electrons. If you put a brighter light, you should get more electrons. A dimmer light, you should get fewer electrons, because the energy of a wave is related to the amplitude. It actually is predicted that a dim light would give a lag time. There's some amount of energy that those electrons need to get before they can get kicked out. And so if the light is weak, if it's dim, they're going to have to take some time to build up enough energy to be ejected. So here's an illustration of the photoelectric effect. You have some sort of a power source, and you have a positive terminal and a negative terminal and a current meter. And we're not really going to see anything happen in this chamber, but we can measure current. In order for current to flow, electrons have to leave the metal surface and travel to the positive terminal. And light is shining in on this, and so we can measure how many electrons are being kicked out by the current. So light comes in, transfers its energy to electrons, and the electrons get kicked out. Well, this is what the experimental observations indicated. So if you look at the rate of electron ejection as a function of the frequency of light, when the frequency is low, you don't get any electrons being kicked out. When you get to a certain point, the number of electrons being emitted jumps up. And this is called the threshold frequency. Up until this point, the intensity of the light doesn't matter. The wavelength matters. The frequency matters. So we come to this point. Now we do see a difference between high intensity and low intensity. But before this threshold frequency, we don't. So the high frequency light from a dim source can cause electron emission without any lag time at all. But low frequency light will not cause emission of electrons at all. So what does this mean? Well, this implies that light is actually a beam of particles. So Einstein proposed that light energy was being delivered to the atoms in packets, little packages. And those packets are called quantums or photons. A photon is a packet of light, a piece of light. It's like a piece of milk, right? It doesn't make a lot of sense. It's a piece of light. The energy of that photon is directly proportional to its frequency. The energy then is inversely proportional to its wavelength. So the energy is equal to some constant times the frequency. This constant is called Planck's constant. It's given the symbol h, and this is the value, 6.626 times 10 to the minus 34 joule seconds. That's not a value that I expect you to memorize. If you need it on an exam, I'll provide that. So this packet of light, the packet's energy depends on the frequency, the wavelength. They're inversely proportional. We can also describe the energy in terms of the wavelength because nu is c over lambda, right? The frequency equals the speed of light over the wavelength. So in this equation, we're just substituting c over lambda for nu. So the energy is Planck's constant times the speed of light divided by the wavelength. So if we look at a 100-watt bulb radiating energy at a rate of 100 joules per second, if all the light is emitted has a wavelength of 525 nanometers, how many photons are being emitted per second? And they're telling us just assume 3 sig figs in this calculation. And then we're also given this bit of information that the watt is power or energy over time. It's a joule per second. So this is where units come in handy. Let's just try to make sense of this. So we have 100 joules per second, and we have 525 nanometers, and we have a 100-watt light bulb. And we're told that watts is equal to joules per second. So 100 watts equals the 100 joules per second. So basically, this is just restating that. How many photons are emitted per second? Well, we have a per second term here, don't we? What is the energy of one of these photons? It's related to the wavelength and the speed of light, right? E equals hc over lambda. Here we have lambda, the wavelength, so we could calculate the energy. Energy would be in joules. We have 100 joules per second, so maybe we could use that to figure out how many photons are emitted per second. So the energy of one photon will be hc over lambda. So h was 6.626 times 10 to the minus 34. Blanking on the unit. Was that joule seconds? Yeah, thanks. Joule seconds. And we need to multiply that by the speed of light, 3.00 times 10 to the 8th meters per second. And then we're going to want that wavelength in meters, aren't we? Because we have meters up here. We want those to cancel out. So 525 nanometers would be 525 times 10 to the minus 9 meters. And then let's look and see what's going to happen with our units. We've got seconds canceling seconds, and we have meters canceling meters. We're going to come out with joules, which is an appropriate unit for energy, so that's probably good. 6.626 EE minus 34 times 3 EE8 divided by 525 EE minus 9. So the energy of one photon is 3.7863 times 10 to the minus 19 joules. We want to know how many photons are emitted per second? There's different ways to think about this. One way to think about this is, well, in 1 second, how many photons? We're looking for number of photons. Well, have we come up with anything that relates photons to seconds? No, we haven't. What does this give us? Seconds to joules. This equals 1 photon. The energy of 1 photon. So that could be used as a conversion factor. So let's see how this works out. 1 second, we want joules per second here. So that's 100 joules per second. And then we want number of photons on top and joules on the bottom. And so that's that energy of a photon that we just calculated. And if we do it like that, seconds cancel and joules cancel. We should end up with a number of photons. 100 divided by 3.7863 EE minus 19. With 3 sig figs, 2.64 times 10 to the 20th. Photons in 1 second. Did I do the math right? Is that a reasonable number? Are photons big things or little things? Little things. A piece of light? It's got to be pretty tiny because we don't see particles in the light, do we? And we've got this energy of 100 joules per second. We're calculating that the energy of 1 photon is this crazy small number of joules, right? If there's 100 joules in a second, there must be a lot of these photons being emitted in 1 second. So 2.64 times 10 to the 20th photons per second. Any questions? Let's look at relationship between wavelength, energy, and frequency. Arrange these 3 colors of visible light, green, red, and blue, in order of increasing wavelength, increasing frequency, and increasing energy per photon, without looking at that diagram. Okay, so this is how I would approach this. I'm just going to think out loud, because I don't have wavelengths of light memorized. There's just, you can't keep everything in your brain. So red, green, and blue. So I'm going to think Roy G. Biv. Right? So I want to put these in order so I've got red, and then green, and then blue. That's the order that they get separated in a rainbow, and that is related to their wavelength, their frequency, and their energy. So for each of these, I really only have 2 choices: red, green, blue, or blue, green, red. It's one way or the other. So wavelength, frequency, energy. Let's do the easiest one first. Now, which one you think is easiest depends on who you are and what you remember. Past blue is violet. Past violet is ultraviolet. Are ultraviolet rays higher in energy? Yeah, they can give you a nasty sunburn. Ultraviolet has higher energy than just regular visible light. So that tells me that the blue light is the highest energy. So this is the highest energy. So then I'm going to answer C first. In order of increasing, that means I put the low energy one first, the middle one, and then the high energy. So energy per photon is going to go red is lower energy than green, which is lower energy than blue. Frequency. I think about ocean waves coming at me. If they're coming more frequently, that's transmitting more energy to me. It's harder to stand up. So energy and frequency are directly related. High frequency, high energy. So then the answer for frequency is the same. Red is smaller than green, and blue is the largest. That's it. Blue. So then we have to come up with wavelength. The length of the wave, because they're traveling at the same speed, a long wave means low frequency. It's inverse, so it's opposite. So answering the wavelength one, I'm going to reverse the order. Blue is the shortest wavelength, and then green, and then red. Any questions? It can seem a little daunting to try to answer a question like that without looking at the table. But if you can remember the order of the rainbow and then have some little memory trigger to help you remember which end is more of something, all you have to do is remember one of them, frequency, energy, or wavelength, and then you can reason the others out. So what I don't think I did a good job of emphasizing is when we were talking about that photoelectric effect. The photoelectric effect is demonstrating that light is a particle. When that particle hits the metal, if the frequency is too low, if the energy is too low, it's not enough to kick an electron out. If the frequency is higher, it has enough energy to kick out an electron. And that's why we see that threshold frequency. One photon, one piece of light at that threshold frequency has just enough energy to dislodge an electron. Why don't the electrons fly off of the metal on their own without being hit by photons? Well, they're bound to the metal. We call that the binding energy. I think this is psi. I keep forgetting the name of some of the Greek letters. Anyway, that guy. That represents the binding energy of the electron. If we irradiate at a higher energy, a higher frequency photon, the electron gets more energy than is necessary to escape. What happens to that energy? It can't just disappear. It's expressed as kinetic energy of the ejected electron. So if you're putting in a photon that has just enough energy to kick an electron out, the electron's just going to come out and just like not be moving much at all. If you have a very high energy, high frequency photon coming in, it's going to kick one electron out, but that electron is going to be moving faster because it's going to have more energy. So the kinetic energy of the electron is equal to the energy that the photon had minus the energy that bound that electron to the metal. So this is like the price you have to pay to get into Disneyland. And this is the total amount of money you have. So the total amount of money, and you've got this binding energy, the money that you need to get in, and then what's left is what you get to spend on souvenirs and food. So you've got the energy of the photon, the kinetic energy. Well, the energy of the photon, I'm sorry, I did that backwards. Rewind. If I actually edited these, I could do that, but I don't have time. I'm sorry. Okay, start over. The energy that the photon has, this is a kid going to Disneyland. I had forgotten about this analogy until I started in the middle of it. The kid's going to Disneyland, he has a certain amount of money. You have to pay to get in, right? Paying to get in is like the binding energy. That's the energy required just to kick that electron out. So this is the energy to get in. After you subtract off what's necessary to get into Disneyland, what you have left over is what you get to spend. Souvenirs, food, whatever. So the energy, the photon coming in, hitting that metal, when you subtract off the binding energy, the energy that's taken up by kicking the electron out, the difference is the amount of kinetic energy that that electron has. The energy of the photon is Planck's constant times nu, the frequency. And we're subtracting psi, the binding energy of the electron. Let's think about this. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if it's struck with ultraviolet light? Well, let's got to remember Roy G. Biv. Which is higher energy, violet or red? Violet, because just past violet is sunburn, right? So this is high energy, which equals high frequency. So here's yellow. Yellow is the threshold for this particular metal. When you strike it with yellow light, you'll get electrons coming off. If you strike it with ultraviolet, ultraviolet is up here, UV. Does that have more energy or less energy than yellow? It's got more. So is it going to kick electrons out? Yeah. So A isn't true. No electrons would be ejected. That would be true for orange or red light or anything below that. So this one's not right. Electrons would be ejected and they would have the same kinetic energy as those ejected by the yellow light. This light that we have coming in has higher energy. E photon is larger. The binding energy is the same. So the difference between the UV light and the binding energy and the yellow light and the binding energy is not the same, right? The UV light's going to carry more energy. So will the electrons have the same kinetic energy as those ejected by yellow light? No. Are they going to have more kinetic energy? Oops. More kinetic energy or less? They're going to have more. Does that make sense at all? It's a weird idea. It's hard to explain. I'm not very good at it. So what we see is that sometimes light behaves like a wave, like in the double slit experiment, the big box, the fringes. Light's behaving like a wave. Other times, the photoelectric effect, light is behaving like a particle. And which behavior you observe depends on the particular experiment. And quantum mechanics would say that when it's not being observed, it's both. But when you observe it, you force it to be one or the other. That's the dead or alive cat.